So let's look at that case of the pillar of rock, um, or this is analogous to what experimentalists will often do. They'll take a drill core, like a cylinder of a rock, and they will subject it to uh, a large stress. And there's something that's observed very frequently is that eventually, you press hard on it again. Of course, if you press hard on it enough, it'll break. It'll fracture. And what's observed is that those fractures tend to form at um, about 30 degrees to the direction of stress. So if we looked at this in 2D, it might be a little bit easier to see it. Um, the plane that they tend to break along um, is at about um, 30 degrees to sigma 1, which in our nomenclature for theta is about um, theta equals 60. Oops. Let's write that down. Rocks tend to fracture at an angle theta equals 60. In other words, 30 degrees to sigma 1. Okay. And that happens, like, it's very predictable. It happens over and over again. And you can sort of, that, and what'll happen, like you're pushing really hard on this thing, right? You're squeezing it from both ends. It's trying to get shorter. So what happens on that fracture is there's a little bit of motion. Okay, as we squeeze it, there's a motion like that. So it allows it to get a little bit, to sort of accommodate that, to strain in a way that reduces the stress a little bit. And the Mohr circle can help us understand that, or sort of visualize it. This is one of the sort of the cool applications of the Mohr circle. We're going to get into this more, but so here's a Mohr circle, say. So that theta equals 60, that corresponds to an angle 2 theta of 120. So this angle we're about to draw, right here, this angle would be 2 theta around 120 degrees.